when you get into air management, a couple of bullet points, if you will. First one is identify air control versus air elimination. The air control is well, we'll explain it, but it's an old school, it's kind of an original approach years ago, and it was very effective for its time. But everything that you guys are going to see, you're going to specify, you're going to design, you're going to walk in mechanical rooms is going to be air elimination. We'll explain that. And then get into what they refer to as the pressure band. And when you're filling a hydronic system, and you got to obviously fill that system with water all the way up, there's going to be a fill pressure. There's going to be relief valves on the heat exchangers or relief valves on chillers or boilers. So there's like a fill pressure, there's a maximum operating pressure, as water temperatures or as water is heated, there's expansion. So there's going to be like a system pressure. So you're going to start cold. You're going to have operation where you're going to have the water heated and expands and increases in pressure. Then you're going to have the safety or that maximum operating pressure, which is your relief valve, stuff that's going to protect the equipment. You don't want system pressures to go beyond X. We'll talk a little bit about how do you establish it. It's something that is pretty simple. You're going to see it and you're going, what's the big deal? You can't believe the number of calls that we get throughout the week, throughout the month, throughout the year, just talking about some of this. Establishing fill pressure, and then how these two guys work together, these two subjects, your fill pressure and your pre-charge of your bladder or diaphragm expansion tank, which is all part of air management. We have to have this body of gas to kind of accept this expansion that's going to take place. As you heat water, the molecules expand, they take up more volume. That volume's got to go somewhere. Water's not compressible. Steel pipe doesn't flex, typically. We'll get into tank sizing, just what's involved with tank sizing and maybe some of the nitty-gritty formulas behind the scenes. And then we'll get into some of the software that's available that we offer, and there are other manufacturers as well. But we'll go through a couple of quick examples with, it's called a SystemWise, Bell & Gossett's ESP Equipment Selection Program, SystemWise. So we'll go through a couple of quick examples. And then one of the other subjects, which is, it kind of sits off to the corner, off to the side, but it's actually pretty important to understand. And then when you're designing or out troubleshooting an existing system, understand the relationship that exists between where your circulator, where your pump or circulator in that closed loop is installed relative to where the expansion tank is and how it can impact positive and negative, the system operation. So we say air management, oh, okay, you got to get rid of the air, but there's a lot to it. There's a lot going on there that's pretty important to the success of how well your system is going to operate. So air and hydronic systems, kind of some, comments, friend or foe, potential problems. Can air bind, can restrict flow in your terminal units, air handler coils, radiation, whatever your terminal unit is, if you've got air that doesn't belong there, it can cause problems, system problems, operational problems. It can cause noise in the valves and piping. Enough of it is being added or exists, can lead to some corrosion. And it can affect that thing we talked about right here, pump tank location. If you've got little pockets of air running around a system acting like mini expansion tanks, it can really mess with the system's pressure reference point. We'll explain that, what that means. What are the benefits of having air in a hydronic system, a closed loop system? Establish that fill pressure, suitable fill pressure. Most importantly, that body of gas is there to absorb, I should say, the expanding water. As you heat it, molecules grow. There's an expansion factor. That's all comes into play with how our expansion tanks are sized properly so that they work, so that relief valves don't dump, and dump excess water onto the floor and then bring in cold makeup water that's full of oxygen, that's very aggressive, that leads to, corrosion. We don't want a system constantly in and out, dumping water, bringing fresh water and dumping. That's not a long-term, solution. That's bad and expensive. And then the other thing about the air, one of the positives would be can provide that reliable pressure reference for the system. So if I have this one pocket in this whole system, a little residential home, large downtown Boston, multi-story office building. I need to have one pressure reference point so that all of my components, specifically circulators, pumps, can do their job properly. They're going to reference that location, that body of gas. We'll get into it. I had showed you that I think the first week we had a couple of live, some actual impellers that we have in one of the shelves here. But air and an unusual amount of oxygen in a hydronic system will lead to corrosion and can also lead to cavitation, which we'll do a number on some of our pump components specifically. So real quick, old original systems. You're not going to see these, although I do, and to be honest with you, out in the field looking at problems around New England, you'll find an old gravity system. Very, very rare. They're almost all gone, but there's still a couple out there. But originally, when we were first introducing hydronics, and where did it start? Here on the East Coast. Started in Boston, started in New York. This is where a lot of the old systems were really originated, late 1800s, and then moving to here we are, 2023. But, so they would have been, they realized quickly that when you heated that coal-fired boiler and you heated the water and it expanded, you had to have a place to put it, or the boiler would explode because water's not compressible. You gotta have a place for that water. So years and years ago, it was just an open tank, an open expansion tank at the very highest point of that church, that school, that house, that whatever it was, that building. And obviously no circulators because it was gravity. Today, everything's closed. Everything you're going to design, like I said, almost every building you're going to walk into, it's going to be a closed hydronic system. It's going to require air separation equipment. You're going to handle air in two methods or two phases or steps. One of them will be right on startup. As you're initially filling the system, what's in the piping and the radiation before you fill it? Obviously air. So we got to get rid of it. We got to displace it. We got to handle it. The second part of that air will be, okay, once I fill it and I do displace all that air through all the terminal units, the piping and all that, what am I using to fill the system with? Water. What is water comprised of? H2O. I've got oxygen that's dissolved. And when I heat it, I'm going to release it. I got to catch that. Entrained air, they'll refer to it as. And I'm going to have some type of pressurization. So I'm pressurizing to fill the system. I'm pressurizing as I heat it. I'm turning a circulator on that's creating a pressure differential that's changing system pressures that you'll be able to read on gauges. And then I also don't want the water to get so hot that I could actually boil the water or create steam formation. So I want to make sure I have enough pressure that I'm above, the pressure point is above the vapor pressure so that that water stays, even if it's really hot, it stays hot water. It doesn't change its state. Avoid pump problems, and then, have a controlled, allowable system pressure. And how do we control it? By how we properly size those expansion tanks to accept that expansion. How much, what's the range, all of those little factors we'll talk about. That will allow that allowable pressure increase to occur without getting excessive and opening up relief valves and all of those things. When you say hot water heat, you mean in a boiler attached to a hydronic system feeding radiation, David, all around throughout a building? Yeah, I was just going to say, years and years ago, before plumbing codes started to change, you didn't have expansion tanks on potable water, the hot water heaters, right? So you got street water coming in, doing its thing. You've got showers calling, so you're open to the atmosphere. You're draining, you're replenishing, you're taking the heat out of your storage tanks, your heating vessels, satisfying your load. And then eventually the load maybe shuts off, and now you got to replenish the tank from what it was. You drained it down, now you got to replenish it. So you heat that water and it expands, right? kind of cheat. Yeah. Yeah, it should have. You would think it would have. But what Will's referring to is that cold water coming into the building. They want it to go through a check. It doesn't go back. Exactly. So originally that code didn't exist. So if the pressure in the system built and it just exceeded the street pressure, no problem. It just moved. And then eventually they say, hey, once the water's in your house, your building, your apartment, I don't want it back on the main. So check it, put a pressure backflow preventer. So then all of a sudden, when they first introduced that, relief valves were dumping left and right because no one knew the correlation of the connection. So either they kind of poke a little hole in the check valve, which is really not what we're supposed to do, but more commonly put in a potable expansion tank that would then in turn accept that expansion, let the pressure rise, but not get to the relief valve that's now weeping water onto the floor. So in a closed loop, and in a potable system, when there's no draw, technically it's a closed loop as well. We want that expansion tank. Yeah. Yes. Real quickly, closed forced circulation, so hot water heating system, closed loop, and they're referencing, see if I can move that without reinventing the wheel, air control. Let's see if I bring that down here. And this is just a reference of older style expansion tanks and what they did years ago. We're not going to do that today. Not that you couldn't, it's just, it's far more easy to move to this air elimination. But they would actually have their first closed expansion tanks, they called them a compression tank. But the point of it all is the system water that's throughout the building and into the tank was actually seeing the cushion of air. There was no butyl diaphragm at the time. It just hadn't been developed or applied to expansion tanks. So it was a little finicky. Really had to dot your I's, cross your T's and all of that on how the system worked. But the main point of air control is you didn't vent it out. You directed it up to this compression tank. And as the system water heated and the air came out of solution, these air bubbles by gravity, buoyancy would direct their way to the tank. The boiler shut off, system cooled down, possibly some of that air got absorbed by the system water, and then we just kind of had this movement in and out of, in solution, out of solution, in solution, out. We didn't want to get rid of it because if we added automatic vents, these are manual vents, but if you had an automatic vent and the vent vented, doing its job, you'd be lowering the system pressure. The reducing valve would see, hey, there's a drop in pressure on my diaphragm. I'm going to add some more makeup water. Well, the only place the makeup water would go would be into this tank. And all of a sudden you're starting to lose that spring. And where the call would come or where someone would recognize it is eventually there'd be no more cushion and our relief valve would dump water onto the floor every time the boiler fired. And they'd say, blah, 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 we got to get it. So that was air control. You controlled the air. You didn't get rid of it. You just controlled it. And there was a way of doing it, but it's not as simple as it is today. And what we've been doing for quite a few years now, it's called air elimination. Now we're using some type of expansion bladder diaphragm tank that does have butyl diaphragm, butyl rubber. So we isolate, we separate air from system water through this diaphragm. So now I don't need to control it. I want to get rid of it. I already got my pocket of air that's going to provide the pressure reference point, expansion, all the value, all the benefits that we want. So now I'm going to have some type of air separating device. And instead of this last picture, which showed that air separating device taking that air and directing it up, I now want to put a high capacity vent, get rid of it. As soon as it's released, because of the water being hotter, air bubbles coming out, get rid of it. Might even have a couple of float vents at the very high point of our system. But I don't care about getting rid of that air. I want to get rid of it because all the air that I need is already contained on the tank side, in this example, on the bladder side from the system water. They're separated through this bladder diaphragm. So, and that's what we do every day, all day. That's what you're going to see. That's what you're going to specify. That's what you're going to come across. So behavior of air in a hydronic system. So a couple of different things. Temperature and pressure influence on air that's entrained in the water. So one example is, listen, if the water is at a constant pressure, as you increase the temperature of that same water, it will release any dissolved air. Now, this is a very simple, kind of a primitive picture, but it's saying, hey, go over to a faucet in the sink in the kitchen, take out a clear glass, fill it with water, and just sit it on the counter. Come back a couple hours later, and you're going to see all these air bubbles kind of attached to the side of the glass. Where did the air come from? You just basically changed the temperature of that water, and it's very subtle. You only went from 50-degree street to 68, 70-degree room, and you release some air. Now make it 40, 50-degree water and make it 180-degree water or 190-degree water. You got a tremendous amount of air coming out of solution. So depending upon the temperature of the water can either absorb the air or it releases it. We want to catch it when we release it. And the other factor, if you will, is at a constant water temperature, if you play with the pressure. If you decrease the pressure, the air comes out of solution. So if I have water at a certain temperature, I have it under pressure, air is absorbed, it's in solution. And if I was to release that pressure, air comes out of solution. So I have two things going on with water, with air, entrained air in water. If I heat it, it will be released. A certain portion of it will be released. If I lower the pressure, air will come out of solution. So I want to think about those two things when I'm designing my air management system, because I want to catch it. I want it where the waters are hottest and possibly maybe where the pressure's the lowest to catch that air. It's a chart here talking about, because really when you get into the makeup of the water, it's 21% oxygen, and then it's about 75, 78% nitrogen. So that's the air bubbles, if you will, that are coming in our solution, because that oxygen over a short period of time will actually form almost like a corrosive layer. It'll dissolve, it'll be absorbed into the piping system and actually cause corrosion. But it's only a small amount. You've got this limited amount of water. You're not constantly replenishing, because that's what the systems get into trouble, is when we have these leaks that aren't detected and makeup water is constantly added. That means there's a bunch of oxygen that's being released and starting to attack. But all it's trying to show here is based on either temperature or pressure. If I keep the pressure at a certain, if I keep the temperature at a certain, constant, as I change the pressure either from 150 pounds and reading down, what they're trying to show here on this chart is the percentage of water that is absorbed, that is soluble, in the water itself. Conversely, if I have a certain pressure, whatever that number is, 50 psi, as I heat the water, so the amount of air that can be held in solution reduces as I increase the temperature. So in our hydronic system, as I heat the water, it's at perhaps before the pumps, I'm not seeing the pump pressure, I'm going to release a lot of air. And I want to have my air separating devices right there. So air management, fill a system. Remove the gross air by venting and purging. So it's quite simple, but literally you gotta fill that system. You got this whole hydronic system here: boiler, expansion tank, air separator, fill valve, some isolation valves, a distribution pump, piping. I got radiation on the first floor, radiation on the second floor, maybe even a third floor. I'm going to use this fill valve. I'm going to bring in system water. I'm going to pass that system water through a pressure reducing valve right here, and I've got to fill that entire system. So I've got to overcome whatever my static height is, and I've got to displace the air. If I'm doing like a pre-mixed glycol, I might be using a pump instead of street pressure, because I've got my water glycol mixture package. So I want to calculate that. What is my requirement? What's my cold static fill pressure to get to the high point in that system? Because that's how I'm going to select what size pump I need to fill that particular building with that glycol water mixture. So I'm either using street pressure, what do I have coming in relative to the height of the building? Or if it's a glycol water mixture, I'm using a pump. I just want to make sure the pump has the capacity to get that water to the high point. Something simple as if I'm filling the system and I don't release that air on initial fill and the air stays, it's gonna kind of get squeezed by the incoming water, but it's not going to disappear, and it's going to reflect down in the basement on the gauge as pressure. And you're going to say, okay, I got the water to the high point, it's under the right pressure. And what they're saying here is if I don't release it, which ideally in this case here, this type of vent, they call it like a coin vent or a manual vent. You'd actually manually open it when you're initially filling. In this case here, maybe like a little flathead screwdriver slot, turn it, open up that coin vent right there. And as you're filling, you'd be releasing that air that right now, in this picture here, kind of got trapped. Didn't get released because someone didn't go around and vent it, but they're just downstairs. They open up the fill valve. They're looking at the gauge going, yep, it's up there. But there's all these pockets of air all over the place that are kind of faking us out. And then when you turn the system on, you might have some air binding and you can't get heated, certain air handlers or pieces of radiation. So on initial spill, they're going to want to address that. And there's different ways of purging. And then you're showing some very simple drawings where I might have my cold system water coming through my pressure reducing valves or station. I have this purge valve where I kind of close it on one side and I open it up to drain. And I might have my water moving in this direction, trying to purge the whole system all the way to floor drain, a bucket, a slot sink, whatever the case may be. That might be one way of purging. Another technique might be, I might be using that pump, some type of pump where I have a kind of a double port, close the valve in the middle, and I'm pulling from this pump, again, moving through and then back to my basket, my bucket to purge it. So the point of it all is I need to fill that system. And as I'm doing it, I want to displace the air. So I want to use the street pressure to kind of push it all the way through. And by isolating one side of that system, it has no choice but to head out that hose right there into that bucket or that floor drain. And these are just like situational stuff that you can come against that will kind of fool you or give the contractor or the facilities guy a hard time. And what they're trying to show here is maybe I got this coil, distilled water, hot water, whatever the case may be. I'm in some kind of cabinet or enclosure. I got a supply pipe through a balance valve of some sort going through, and here's my return line. And they're just showing an example where you turn the pump on and the pump's differential across this particular circuit, this terminal unit, can develop 2 feet ahead. But to displace all this air that mistakenly was left behind, I need to overcome 6 feet. So I displace 2 feet. So the pump's doing its job. You'll say, hey, I got circulation. What's going on? And I don't have circulation through this particular unit. One of the ways to address it would be make sure that at least that pump head dedicated to the circuit is at least the height of this piping arrangement here. If I can just displace the 6 feet, I might not get all of it, but I get a good portion of it to the point where I have circulation through that coil. So 2 foot ahead across it, pump does its 2 foot differential on that circuit, water rises, but it doesn't displace all that air. Change the head differential to match the piping and coil arrangement, and I can use that pump's head as a purge to unload that coil. A better, or perhaps even a better, is to increase that differential greater than 6 feet. And so that when I turn that pump on, I absolutely unload every piece of pipe, as opposed to I got this little pocket left over. In this example here, maybe I set it for 8 or 10 feet. So I dedicate a higher than the piping differential between the inlet and the height for the outlet, the return pipe. And I can use the pump's operation as a purge, just using its head differential. So good piping designs on some of these fan coil or any kind of terminal unit, but avoid air traps, ensure automatic purging at full flow, keep the velocity high enough We talked a little bit about that on scale 3 on system size last week. Velocity, I want to make sure that it's at least above 2 feet. 3 to 4 to 5 is a good design range. And it's just to keep the velocity high enough to carry the air. And then obviously balancing through all the different terminals, make sure I have flow through all my units. So I filled the system, I vented it, purged it. Now I'm operating. Now what do? I got different temperatures, I got pressures, I got velocities. How do I handle the air that's in the water that I use to fill the system? And now I'm going to heat it. So air separating equipment. We touched on this the first week just as components that you're gonna come across. Air separation and air removal during normal operation. Where are they recommended? Well, we just talked about when the water's the warmest, it can't hold air. And when you drop the pressure on the water, it can't hold air in solution. So those are two favorable locations, where the water's the warmest and where the pressure's the lowest. The air release connections, everything that we're going to talk about, what you guys are going to see in design moving forward is going to be here. Air elimination. We mentioned it real briefly, that air control was where they would direct it. They'd control the air from that air separating device up to the tank. But these devices, I want some type of high capacity vent, get rid of it. So like in a heating system, and that's what they're trying to show here on a very simple drawing to the left. Where's the water the warmest? Right after its heat source. Simple enough. The boiler, air separator. Over here, they're trying to show us a drawing. Maybe this is a chilled water application. It's a chilled water plant. And I still need an expansion tank because there's going to be a change in temperature. Typically, when the chill is working, I'm actually lowering the water temperature, right? So where is the most expansion? Where's the water the warmest in a chilled water system? Yeah, it's on the return. It's typically on the return. And then if the chillers for some reason were off and they actually experience ambient temperature, it could be as warm as 80, 85, 90 degrees. That's going to be the greatest expansion. So expansion tanks do play a role in a chilled water system as well. The expansion isn't as great because the temperature range isn't as great, but there is expansion that you want to be aware of. My air separating device, again, would be on that return, going back to the chiller plant. Water's the warmest on the return of a chiller. Water's the warmest on the supply coming out of my boiler plant. Very simple device, an air scoop, an inline air separator, just uses velocity. Flow the water down. It's an engineered device. A lot of the contractors look at it and say, yeah, it's a pretty simple, what's your price? Do you have them in stock? That's the extent of it. What size pipe? And then they engineered this body diameter to affect the velocity so that it went from 4 to 5 feet per second to a half a foot per second, 6 inches per second. So it really slowed down. So they gave the chance for the air bubbles to separate and then vent out a high capacity vent. And the next device, very common commercial applications especially, and it's becoming more and more common, is this enhanced air separator, coalescing device, where it has almost like these stainless steel coalescing media, the surface. And the whole idea is, especially if you have all of these small, or sometimes you might hear it in the industry called micro bubble, all these smaller air bubbles that are being released. They're really not that big in and of themselves. They don't have the buoyancy, perhaps. But if I give it enough surface area, all of these small little bubbles will gather and they'll become bigger bubbles, literally. And then inside this kind of this lower velocity, lower pressure chamber, they will be released out through a high capacity vent at the top. So I got all of this surface area here to kind of collect any of those air bubbles that are coming in, good, big or small, gather on this media, and then eventually be buoyant enough and get released. Very popular, very common in commercial application. The probably most popular style that you're going to see is this kind of a roll air troll or a centrifugal air separator. And sometimes you'll hear the expression, it's a tangential air separator. And it creates almost like this centrifugal action in the inlet port and the outlet port. The way they're connected or mounted on this chamber, if you will, is they're on the outer edge of one side of this vessel, this tank or this cylindrical vessel. So as it comes in, the heavier air-free water kind of gets flung along the outside edge, and it creates this centrifugal force chasing after the outlet or down here. So I'm coming in, heavier water flung around the outer edges, chasing after the suction of that pump. That's your low pressure. High pressure goes to low, it's going to the suction. And the lighter air gathers, and there's in the middle, there's like this stainless steel collector tube. And it's low velocity, and it will collect it and just get released through a high capacity vent. It's very effective, been around a long time, but it does a really good job. And that's, again, another very common device that you will see and probably specify in the commercial space. Kind of the newest guide to the market or to the arena is this this primary secondary header, or a low loss separator. I apologize to everyone that's online, but I'm standing here in the classroom holding a very small version of it. But it's just a, sometimes, like I said, they'll call it a primary secondary header. We're going to get into primary secondary later on tonight. But it's a low velocity area, typically used with boilers. So I might have my boiler plant on one side, hot in, cold out to the back to the boiler. System side, hot out to the system, cold return coming back. It's a convenient location. But because of the low velocity to provide that low pressure drop for my primary secondary connections, which we'll explain in more detail later, the manufacturer said, hey, that's a pretty good spot to also collect any air coming out of solution out of my hot boiler water. So I'll collect it right here, put a high capacity vent on the top, get rid of my air, act as my primary secondary tees. So I'm kind of killing a couple of different functions with this one device. The third thing, some guys take advantage of it, some of them do not. But again, because of that low velocity, not only can I collect any of the air that comes out of solution and vent it, as I'm coming back from the system, if I have any sediment, almost like dirt sediment or scale sediment coming back in the pumped flow, and all of a sudden it hits this wide, slow, low velocity area, those little dirt sediment will fall to the bottom, where the guys will install a blowdown valve and they could blow it down. Yes. Well, there might be some mixing, just like a primary secondary tees, depending upon flow on this side and flow on this side, which we will hit quite heavily in about an hour. But yeah, so there could be, by design, it's Mother Nature. It's just, you got X coming in and you got Y going out, and they're not exact, then yeah, there could be some mixing, and that's very normal. That's very normal. Well, the whole connection. Oh, I'm sorry. Yes, everyone remotely. The question was, can this be referred to possibly as a decoupler? And the answer would be yes. And that's a kind of common, whether it's this low loss separator, primary secondary header, low loss separator, decoupler. And the point of that word decoupling is I'm decoupling one loop, say the boiler plant, decoupling it from the distribution, because what will happen as we get into primary secondary is I'll have pumps on one side that are pumping the boiler plant, then I'll have distribution pumps. And I don't ever want to see those guys fighting each other or in series with each other. So this device, just like regular primary secondary tees, will decouple my pumping on this side relative to my pumping on the system side. So yes. Correct. Right. So from air separation, low velocity, little scoops, coalescing mediums, those inline coalescing air separators, centrifugal, roll air troll, air separating devices or tangential air separators. And then this last one here is, again, like I said, it's kind of like the latest technology to enter into that market is these low velocity primary, secondary headers. And there's a bunch of different manufacturers. We're one of them, Bell and Gossett, but there are others out there. And it really was kind of promoted with the boiler plants. So 2, 3, maybe a multiple boiler plant, connecting it to a distribution system. I got to separate the air anyways. That's my hottest spot. Why don't I use my primary, secondary connections and my air separating devices all in one? And that's how it came to be. I keep mentioning air elimination. I'm going to have vents. So I'm going to have some type of automatic air vent on the top of all of these various devices. Something sitting up at the top of that tangential roll air troll at my low loss header, primary, secondary header. Going to be any one of these. Obviously, the smaller ones are probably more suited to a residential, lower volume system. And then I move over here to a really commercial grade, high capacity float vent, automatic float vent. But any one of them will have some type of float with like a little lever connected to the port or the seat in that. And as that float inside there gets, I apologize, I'm showing the people in the room here, and I know you guys online can't see, but there's a float inside here. And if if the water around it gets displaced with enough air, then the weight of that float starts to drop down. And as it does, it pulls on that lever, which opens up the port on any one of these devices. Now I got system pressure behind, pushes the air bubbles out. The pressure displaces the air, float rises back up, the port closes. That's all it is it sees this volume of air, which is lighter, different than the water, the float can drops. Pulls it with its lever, pulls the port open, system pressure shoves the air out, float replenishes, closes it. So you're not leaking water on the floor. That's the last thing you want, is water coming out of these, whether it's down in the mechanical room or in your high rise, rises at the very top. So again, optimal location for air separation, water the warmest, pressure the lowest. Pressurizing equipment. How am I, what am I doing? What am I using? I'm using pressure reducing valves, is what we're trying to show here on the left-hand side. And then if I had some type of glycol package or glycol makeup package, I might have a storage tank of some sort, maybe even a panel, and then an expansion tank, and then some type of pump. That pump's going to be sized, obviously, for the flow, but also the pressure. How tall of a building am I attaching it to so that I can fill and pressurize that complete system? On the relief side, the other pressure component is going to be your pressure relief valve. I'm there, hopefully never operating, only because the system conditions have never got to the point where I need to come into play. But if it does, I want to make sure that this thing can do its job to protect, to release any buildup, so we don't have issues or problems with explosion. They're very rare. And as technology has gotten better over the years, it's even less and less. Years and years ago, it wasn't as uncommon to have a boiler explosion, be a steam boiler or a hot water boiler, for various problems, various reasons that occurred. But what they're just trying to show here in a quick glance is when you're dealing with these relief valves, whether on boilers or on heat exchangers or whatever the component is, the manufacturer says, hey, I don't want to operate above X, a certain pressure. There's going to be two settings that you want to contend with, especially on the boiler side. One is, okay, what does the manufacturer say is my maximum pressure? I don't want to see pressure above X. This is all I've been tested for. This is all I'm rated for. So here on that left-hand side, relief valve, relief setting PSIG. So pressure. But over here, it's saying I'm attached to a certain boiler that can only operate up to 30 pounds or 75 pounds. That's fine. How many BTUs? What's my energy that I can produce? Because when I do go to relieve because of a system condition, I got to make sure that that valve, that port, that orifice is big enough to release that energy. If I open up because of pressure, but I can't get rid of the energy fast enough, that pressure still builds. And the valve almost doesn't do its job because it's undersized, not from a pressure, but from a BTU capacity. So there's kind of a two checks. One is the pressure, 30, 50, 75, 100, whatever. What are the BTUs per hour? So make sure the valve exceeds the boiler capability and has the pressure rating that the manufacturer says, hey, I'm a 30-pound little cast iron sectional boiler in downtown Boston. Don't put a 50-pound valve on me, just because you can. Haven't been tested. God forbid anything ever happened down there, something, and they come back and you have the insurance people come in and say, who the hell put a 50-pound valve on a boiler that's only been rated and tested by the manufacturer in the industry for 30? That's a problem. That's a serious problem. So you never want to play with that. And again, having said all of this, hopefully they never activate, because the system conditions and we've designed everything and the product's all working properly. They just kind of sit off the side and don't do anything. That's good. But if they do need to go or need to be active, then make sure we have the right ones. So roller air management tank. Again, here's that old air control compression. We really want to focus down here. These are our residential and our commercial ASME and non-ASME diaphragm and bladder tanks that we're going to use. They're going to perform system pressure reference point, retain surplus fluid, right? Thermal expansion. 1,000 gallons of water at 40 degrees, it becomes 1,000 gallons at 180. It's going to expand. I got to have it go somewhere. It's going to go into one of these tanks by design. We're going to select the tank to do that. So I want to have that surplus be able to enter it. And then as it's entering it, keep the system pressure below the relief valve that we just talked about. That's our max. We don't want that active. So the job of this guy is to make sure that that system stays closed, under pressure, closed, but safe. These are just some of the weird components. No, they shouldn't say weird. These are some of the components that would have been needed years ago when they were talking about these old air control tanks. It was really had to dot your I's, cross your T's. It would work, but there's so much to it. So it's so finicky that the industry X number of years ago, and I mean years ago, moved away from this and went to the this type of diaphragm or bladder. When I keep saying bladder or diaphragm, in this case here, it's not a full acceptance. It'll be an expression you hear. Both we'll talk about tonight. You'll see it in some of the manuals. Then as you get online, you start doing selections. They'll start talking about the tanks that you've selected, and they'll say full acceptance, limited acceptance, diaphragm or bladder. We'll talk a little bit about that, what that's all about. But the main thing about the benefit of these tanks is the air that we need, that we were using in these old style tanks, they don't see each other. The system water and the air are separated, which is a good thing. And the other thing about the tanks is they can be smaller. For the same system, when you did an older style tank, you're already starting with 55% of that tank's volume is filled with water. When you go to this style tank, any one of these style tanks, there's no system water in that tank when it's cold. It's only when it gets hot. When you first put that system in, that system's cold and it's got 50. And the other thing is this had to be mounted up high in the rafters above, in the mechanical room, but up at the ceiling of the mechanical room above the heat source, the boiler, because the air was going by buoyancy, by gravity. You couldn't take that tank and put it down on the floor, because how in hell are you going to get that air to go down? It wouldn't. Here, I don't need that air. I want to get rid of that air. So I can put that tank wherever I need to. It can be right beside it. It can be off to the side. I can put it mounted on a bracket. I can do a lot with it. It gives me a lot of flexibility in the mechanical room and still perform all the things we're going to talk about. So that's, there's just a lot of benefits to why the industry went this way, air elimination. Just a quick note on the B and G tanks, only because that's what we represent, Bell and Gossett. They're coming from the factory pre-charged now to 40 PSI. We want to be aware of that. We're going to have a deep conversation about that, just to be aware. Because as these tanks get specified, get bid on, and a job gets awarded, and then the equipment shows up, and then the mechanical goes out, and he builds the system, puts it together. There is a couple of very subtle procedures that take place when that tank gets installed that they got to really pay attention to how they pre-charge that tank so that it works the way you specified it and designed it to work. So that pre-charge of 40 might not be the right charge for 90% of the jobs it goes on. So they're going to be responsible on day one when they're installing to address that. We'll talk a little bit about that, but that's important because a lot of times the guys downstairs will get the call after a job's commissioned and all of a sudden relief valves are blowing. Something's wrong with your tank. We think the bladder's busted. I'm like, well, that happens. Things happen. Why do you say that? Well, we just, filled the system, attached it. We just fired the boiler plant, pressure rose, relief valves dumping water all over the place. I'm like, okay, well, how tall? Tell us the fill. Yeah, okay, we got the fill. All right, what'd you pre-charge the tank to? Silence, Oh, it's whatever the factory set it for. The factory, the factory has no idea where these tanks are going across the United States. To what buildings, the height, system height, where's the tank going to be? That's up to us, designing it, and then the installing to follow those directions to put it in correctly. So again, real subtle, so important. So you just want to be aware of it. Very simple little drawing, little, colored line drawing, but what they're trying to show here is, here's my hot coming out of my heat exchanger, my boiler going to my air separating device. I have my high capacity vent. I have my pressure reducing. Here's my cold water line coming in on that line. Here is my bladder or my diaphragm. And either one could be up or down. It doesn't matter. They're just showing two different examples. Diaphragm up here, bladder. But they're showing this thing here. Recommended anti-thermal siphon loop to prevent gravity heating of the tank contents. So this hot water, if I just put the tank right there or tied it in right there, the tank could cease that hot water. And that hot water goes in and it expands, right? And it can affect the size of the tank. So by putting this little anti-thermal trap, either way, whether I'm going from the bladder that's sitting on the floor or the diaphragm that's elevated, instead of going right off that pipe up to the tank, introduce this little thermal trap. All of the installation manuals reference it. The point is to keep the heat away from the tank. It will just it'll heat the water, it'll heat the air in the tank. Technically, it could cause the tank to be bigger than it needs to be. So they always have that reference. Use that anti-thermal siphon loop. And then these are just little valves connections. But the convenience of it is, if I have a way of connecting a tank, I have a way of isolating the tank from the system, and I have a drain. After it's out in the field and there's some issues going on and someone says, hey, we're going to troubleshoot it, what's the pre-charge of that tank? Well, if that tank's connected to the system's live, and someone just walks over with some type of pressure gauge and reads it, it's going to read whatever the system pressure is. You got to isolate it. So they'll close that valve and isolate it. But then you got to drain the pressure that's built up inside, say, that bladder. You got to unload that so that you're truly just reading the air charge while it's disconnected from the system. So these little kind of multi-purpose valves that the mechanicals use all the time is a nice way of being able to install the tank either way, and then be able to service it. And then if need be, with the union, we're able to replace the tank, replace it without affecting anything else within the system, because I can isolate the system from that tank. So it's a real convenient device. Instead of just sticking the pipe in, because technically that's all it needs to operate. But when you think about how do I service it, how do I check it, how do I remove it, give yourself some of this serviceability. This is just a quick comment. You guys are never going to be tasked with doing this. It's going to be more than a mechanical contractor. And we even tell them, ideally, maybe not even do that, just go to get a replacement tank. But what they're talking about is one of the selling features years ago with these full acceptance bladder tanks is you could replace the bladder. You could actually, if a bladder bursts for whatever reason, stress, time, age, whatever, instead of buying the whole tank, you could just disassemble, kind of take that tank, put it on its side, take the flange off, and pull this bladder out, and then try to get a new one in. Miserable. That's a very good word. Get a replacement tank. It's just the labor. It's not worth it. It really isn't. It's real heavy. a nightmare, to Will's point. It really is. And the thing is, you experienced it, right? Yeah. But it's so real when you're like with 2 or 3 guys that got wrenches that like to beat the hell out of you, you know, because it's just easy, replace the bladder. And it's hard. Never again. One and done. And a lot of the guys that work here over the years, they'll say the exact same thing. It's the exact same experience. It sounds good sitting there. You can even get on YouTube and see this little thing in the factory and everything's conditions are perfect. And the guy, don't do it. Don't recommend it. Right, right. And that's a good point. We'll talk a little bit about it, but when you go to size and select, just because the program picked out this one big monster tank that will do the job, down the road, how do I service it? How do I address it? Maybe 2 or 3 smaller ones gives me a lot of less pain, agita down the road when things go wrong or things finally fail, because they do eventually, something happens. Anyways. So allowable pressure range in the system. So what pressures are we talking about? Well, you got a cold fill. So the system's cold. I haven't heated it up. I'm just filling it. What do I need? Operating pressure. Okay, now the boiler is running. I've heated the water. There's going to be a different pressure that I'm going to read. And then the last one here is, okay, I turn the pump on. Pump creates this pressure differential. Ideally, it's going to be additive. I want to see that. How does that change the pressure in the system? So they got these, I mean, to me, these are splitting hairs right here, R, L, D, and H. When we talk about it, and we typically will get on the computer and do our selection, these guys are all so close to each other. The relief valve on the boiler, the fill valve, the expansion tank sitting right there. Typically, we'll use the same number. They're getting very exact, and that's okay. I mean, it's good to be aware, but typically they're all so close to each other. All of these things that we're referencing with these gauges or these pressures. Expansion tank, makeup, which is a cold water line, pump suction, it's sitting right in that same general vicinity. The relief valve off of your heat exchanger, in this case, your boiler, they're all right next to each other. So cold fill, really, and I think we might have briefly touched this on our component night, the first night, but cold static fill or initial system pressure is just a function of how tall is the system. From the typically, where is this device? Maybe it's down the mechanical room. How far, how long, how high to get to that highest piece of piping or radiation in feet? That's typically what we need to calculate. I guess just before we get that, you know, the fill pressure does a couple things. Obviously, fills all the radiation. We want to make sure we have water there. It's a hydronic system. Provides venting pressure. We'll talk about that. Prevents fluid boiling. That's kind of an extreme, but if you were running some higher temperature water, you can use the system pressure to make sure the water stays water. It doesn't get, like if the pressure is lower and the water is hot enough, it'll flash. All of a sudden, you got steam, you get issues. And then ideally also avoid any cavitational, any pump problem. So most systems that we're talking about, and this chart is in, let me reference it real quick. And for those that are at home that will be getting these catalogs, there is an air management catalog referenced as a TEH 1196. And then there'll be another one we'll talk about later, the primary, secondary. But just about everything that we're referencing tonight, a combination of one, you're going to get a copy of this presentation in the PDF. David will have that Dropbox link. So have you guys all got that email last week? So whether you choose to look at it or not, it's fine, but you have access to it. Same thing will hold true with this. So what this chart, without spending a tremendous amount of time, all it's trying to show us is there's like this safety margin, like water at 210 will boil. I mean, if you're running water at 210 degrees, have a fill pressure of 4 pounds on the pump suction, minimum pressurization at the pump. And then as water gets hotter, they're saying, hey, maybe I want to have a initial pressure higher than that. What they're not taking into account, which all works as a benefit to us, is a lot of times the mechanical room's down in the basement. And I have all of this vertical static height, weight of the water sitting on me. That's a positive. The only time this gets really important is sometimes they'll have the mechanical room up in the penthouse. That's the highest point. So all the weight of the water is down below, but it's not helping my pumps if they're up in the mechanical room. So if I'm dealing with really hot water in that mechanical room, I'm going to start paying attention to what's my fill pressure, right? How do I set it? Because it's really not about filling the building, because if I get water at the high point, I got it at the low point. It's all about protecting the pumps potentially if I start getting into that higher water temperature as my operating, which is not that common anymore. Typically, we're going lower temperature, you know, as a general theme, but it's just something to be aware of. So here, real quickly, just throwing some quick numbers, a little residential, maybe two-story home. What the numbers are in feet, and all we're going to do is say, hey, add it up, 18.5 feet divided by that 2.31 we talked about, where that comes from. It's 8 PSI. So I'm going to set my PRV to 8 PSI. And that gets water to the high point, which is what I'm trying to achieve, right? That's good. I got water all the way up to my highest piece of radiation. But what I'm lacking is what's the pressure at the high point. If I do the math and divide it and set the valve accurately, it's at 0. So if I had some hot water running around there, or if I had vents, and a vent goes to, that float goes to open, if I get some air around that float, and at the high point I have 0 in the system, what's the pressure on the outside of that vent? Same, 0, no motive force. So an industry standard was always, whatever it takes to get to that high point, add 4. You'll see it written everywhere, all over the industry, add at least 4 to 5, it can't hurt. But now, at least if I have that vent up there, those vents, and I have this body of air, bubbles gather around that can, and the can falls down, gets displaced by the weight, I've got 4 pounds of pressure going to 0. So I got motive force to get rid of the air. So whatever it takes in height, add 4. That becomes my fill valve setting down here in the basement. It's quite simple. It's in the manual. Pressure ranges, pressure limit components, the allowable pressure range. Upper limit's going to be a safety release. Lower is your pressure reducing. So when the system's cold, this is what establishes my fill. I want to make sure when I operate, and that means heat the water, size my expansion tanks, this guy's not active. I don't want him active. So standard conditions, maybe, maybe not, but 12-pound fill would be a standard condition for a 2-story application. Could be a 2-story office, could be a 2-story home, it could be a 2-story apartment, 2 stories. You do the math, takes about 8 pounds from the basement to the high point. Add your 4, there's your 12. Almost every valve, pressure reducing valve manufacturer in the market, when those valves come out of the box from the supply house out to the field, out to the industry, to the application, to the job site, they're pre-charged to 12. That's the reason. Just the majority of applications are going across the country, are going into a 2-story. That doesn't mean they're all going to 2-story. So if I go to that 3-story or 4-story, well, that 12 is no good. I got to adjust it. I got to increase it to get the water to the high point, like we just talked about. And then most residential applications are going to have a 30-pound relief valve on the boiler. Not all, but most. That's all you need is the 30 pounds. So those are kind of your 2 ranges. Filling it at 12, maximum allowable. Don't get past that 30. I don't want that valve opening up. Expansion tank, you know, I'm not going to have any water in that tank. I'm just going to have air, the air charge, which it has to match the system fill pressure, which we just talked about. So residentially speaking, those diaphragm tanks, we got hundreds of them out back, and all the other tank manufacturers that are distributed throughout New England here, they're all coming from the factory pre-charged to 12, just because the majority of the applications are a 2-story building. It's just industry standard. So these residential stuff, not the commercial, but the residential, they're going to come 12 on the fill valve and they're going to come 12 on the tank. You take that information and you go to a 4-story building, those two numbers don't work. And you got to acknowledge that. Operating pressure increase. The heat is added. And all this is, again, one of these little charts. We're going to talk about it. It ties into our software when we select tanks. But there's this water expansion factor. And there's some calculations that were done a long, long time ago. But what they're saying here is, and this is a quick number that I've always just remembered in the back of my mind, if I'm dealing with 200-degree water, I have a 0.035 expansion factor. So if I had 1,000 gallons of water, I would take that 1,000 times 0.035, and I know the expanded volume of water. That's part of the equation to size the right tank. Where am I getting that? I'm just looking over here, percentage increase in volume. So 1%, 2%, 3, 4, 5, 6. So 200, halfway between 3 and 4, there's my 0.035. Just an easy, quick number, remember it all the time. You're out in the field saying, is that 10? Well, you know, I can do a quick formula. Or you can have it on your computer or your iPad or whatever. But that's what they're referencing. So Boyle's law, and when it's talking about gas and how the behavior of gas changes. So what they're saying here is a quick example as at the temperature is constant, then the volume of gas is inversely proportional to the pressure exerted on the gas. So if I squeeze the gas, so the volume starts to shrink, the pressure goes up. Conversely, if I was to take the pressure off, then the volume would expand. So all they're saying here is, you know, if I have a same temperature and a certain pressure and I put more pressure, that volume has got to increase it. And that's kind of a neat little picture. It's very simple, but that's talking about what happens in an expansion tank, whether it's this little silly little residential one or X number of, you know, hundreds of gallon diaphragm, big commercial ASME tank. When you attach it to the system and the system's cold, there's no water in that tank. That's how you sized it. That's how we want to size it. And then as they heat the water, now that water expands. And as it expands, how much? Well, how hot's the water getting? There's my expansion factor. It's going to start to enter in and it's going to fill that tank. And as it's doing so, what is it doing to the air pressure? Squeezing it. So it's raising the pressure. So you could look down on a mechanical and look on a gauge, and as the boiler's firing and the pressure's climbing, you're just watching the air getting squeezed. That's reflecting the increase in pressure in the system. And the whole key is just make sure it stays below our relief valve, and we're good to go. Everything's going to be fine. So volume goes down, pressure goes up. Why is the volume going down? Because I'm heating the water and water's entering the tank. So that body of gas that I have, that doesn't change. It's separated by that butyl diaphragm. So it's always there. It's just increasing or decreasing in volume based on the water pressing it. And conversely, what happens when I turn the boiler off and the energy starts to dissipate? This spring presses, unloads the water out of the tank because the water's kind of contracting because it's shrinking the molecules because it's losing its energy. It's just, this is kind of a busy chart, you know, we'll go over it. I mean, you can go over it on your own, but it's just talking about the impact. When you're, at the end of the day, what this chart says is, if, as you calculate, do your calculations, and if you pick the absolute smallest tank, that will work, and it will work. If any other system conditions change that you weren't aware of, it could hurt you. It could hurt the operation of the system. So sometimes picking that least expensive, maybe got the job because I was least expensive, but if something changes out in the field and someone changes the aquastat setting and turns the water temperature up, someone changes the relief valve on the boilers that got ordered different from what you thought was going to be out, all these different things. So it can have an impact. Larger tanks, a little more money, a little more flexibility, a little more range. And then just going through some examples here. How you can get in trouble. But pre-charge, what's the big deal? We've kind of hinted at it. But these are just two good scenarios because we'll get asked the question a lot, especially from the field. from the contractor. If the tank precharge is too low, what can go wrong? So the system's empty, the tank's at a precharge, and I fill the system. And what have I done? I've taken my pressure reducing valve and I've adjusted it for what? Say it again. Yeah, for the appropriate pressure that I need. How tall is my building? And what we're saying here is the tank precharge is too low. That means, oops, someone forgot to precharge the tank to match that. Now the system's cold and you're filling it. Where's some of the water going that doesn't belong there? Remember that picture I was showing you? I hate to go back too many. When that's connected, there's no system water here. It's only when you start firing the boiler and introducing heat and the water molecules are expanding and the water volume expands. When you're attaching it to a system, no water in that tank. So now when I undercharge the tank relative to the fill valve, water comes in. And everything's fine at this point. Everything's still fine. But now what happens is I'm at design temperature. I've got maximum expansion of water. And I don't have the room in the end to accept all that water. The pressure takes off like a rocket and my safety relief valve discharges, or the tank diaphragm bladder ruptures. To Will's point, and all of a sudden now I got this bladder I'm trying to, and I don't want to do that. But they work hand in hand. Precharge, the fill valve setting and the precharge of the tank, hand in hand. They're very important. And then the guy says, you know what, can I beat the system? What happens if I put too much pressure in it? I'll overcharge it. So it'll be fine. It'll be more than I need. And guys will do that. They'll take the time to actually put the energy into, I know I only need 12, I'm going to put 20 in here before I attach it to the system. So then you go and you fill the system, fill it up appropriately, set the valve, no water in the tank. That's good, that's okay, but it can't. Maybe he's set at 12 and he's at 20. There's no way 12 can get into 20. It's not gonna. Now you start to heat it and the water still can't get in because it's not up to that 20 yet. And then eventually it does get past that and it starts entering, but the pressure in the system's already, you've defeated the purpose. It's already hit your relief valve. It's already dumping. Discharge can occur. So you can't beat the system by undercharging, and you definitely can't beat it by overcharging. They all work together. Mother Nature is very honest. Just kind of do the right thing. That's all. How does pump head influence system pressure? So here they're just showing, here's my operating pressures. What's my precharge? Height, right? Divided by 2.31. That's my pressure. And then I add the 4. Why do I want the 4? So I want positive pressure at the high point, industry standard. That becomes my precharge. And I have, a relief valve. I can see it on the gauges, what's going on both sides of the pump with the pump off. Pressure's reading the exact same. And then I heat the water, but the pump is still off. Gauge pressures are going to start to change because of doing it. The water's expanding, the expansion tank's doing its thing, but the relief valve isn't dumping. And then I turn the pump on. And then I look at this gauge here, and it's higher than the suction. And all it's reflecting is the energy, because you sat down, or someone on a computer said, hey, I need to move 200 gallons a minute at 50 feet ahead, which is, round numbers, 23 PSI. So I'm going to see a 23 PSI increase on this gauge relative to when it's off, and I'm just seeing fill pressure. So that's another gauge pressure you're going to read out in the field you want to be aware of. All the pump head must be used up. And all it's saying here is whatever it can develop, when it turns on, if you have that gauge right at that discharge, right at that discharge, and you put gauges across the system, you're going to see it slowly drop. Why? Why is it dropping? It has to. Yeah, friction. I'm eating up the energy of the pump head that I had calculated that I needed to move that flow to overcome the frictional resistance of my heat exchangers, my fan coils, my piping, all the above. So what that's trying to reflect here is, it's not that maybe the pump went to 0. He just went back to non-operating system fill pressure, that red. But everything that he can develop gets eaten up. Remember when we kept harping about the pump curve and the system curve? They got to intersect. That pump is going to pump as much as it can based on the pressure differential it can create, because by the time it gets back to the suction, it's all eaten up. There's no leftover energy. I haven't put it in my back pocket and saved it for a rainy day. It's gone. There's no leftover. So the idea is, if I size it right, there is none, and I've moved the appropriate flow rate through the terminal units. So what's the system pressure? Really, it all depends on where you're asking me. Is it the top of the system, the bottom? Is it hot or cold? Is the pump? Those have all impact on what's going on. Real quickly, I mentioned at the beginning, the point of no pressure change, where the pump is located relative to where the expansion tank is connected to that system can really have an impact on how well or not so well that pump's pressure differential worked. And so again, just kind of going through a system, I've got it filled, no temperature, the pump is off, there's no water in that pre-charge tank because it's set properly to that setting and that charge is the same. And when I turn the pump on, what they're trying to show here, it's a little bit, it's a little clunky, if you will, but to change the pressure, in this tank, I have to change the volume of air. So to change the volume of air, I have to change the volume of water. So I got to get some water to move into that tank, because if I did, what would happen to the volume of air? It would start to squeeze, right? And the pressure would rise. But if I have a cold system and I just simply turn the pump on, I haven't changed the volume of water, which means I haven't changed the volume of air, which means I haven't changed its pressure. So you'll keep hearing that expression right there, the point of no pressure change. Wherever an expansion tank, any expansion tank that you guys design, specify, have a mechanical contractor bid and install, where that tank connects to the system is referred to as that point of no pressure change. We always want our pumps located such that they're pumping away from that point, so that its head differential is always additive to the system. There's no drop. So V1 equals V2. There's been no change of air. There's no change in pressure. P1 is equal to P2. No pressure, no change in pressure due to pump operation. Now, pump is off and I heat the water. What's going to happen? It's going to be a change in pressure in the tank. Yeah, because I squeezed the air because I've displaced it with some volume of water. So technically that connection right here, that pressure does change, but it changes because of thermal, because I've heated the water and it expands. Pump is off. Oops. Turn the pump on. And I still haven't changed the volume of water in the system. That volume here was a function of the heat turning on, the boiler's turning on, heating the water. But simply turning a pump on doesn't change the volume. So that reference point, that point of no pressure change, very important. And I bet you in most of your firms, when you go back, you'll have these designs, these standards, and you're going to see that all of your pumps, whether they're inline, whether they're the big base mounted pumps, they're almost always going to be located. So they're pumping away from your air separating devices. And right beside that is going to be your connection, your line to your some type of bladder or diaphragm tank. It's been known for a long time, but sometimes if it gets overlooked or misunderstood, the pumps can, all of a sudden operate. Here's a quick scenario. If for some reason someone didn't realize it and they were pumping at the point of no pressure change, now I'm not changing the volume of water in that tank, right? So I'm not changing the volume of air, so I can't change the pressure. So that differential the pump generates can't increase. So I didn't change the volume of water, so I didn't change the volume of air. So the differential now shows up as a drop in suction pressure. So you have a gauge on the pump, suction and discharge. You turn the pump on in this orientation and the suction gauge drops. It's like pretty, until you see it, you don't even believe it. But when it happens, And all of a sudden you get vents at the high point in your system. And when there's drop in pressure, the vents do this. The can falls in and air comes rushing into the system just because you turn the pump on. It's pretty powerful stuff. And it was actually because of all those problems that they really discovered and said, hey, where this tank connection is very important relative to the pump's differential. Can it be additive or subtractive? We always want it to be additive. Positively pressurize the system. It's back down to zero here. Yes, zero differential, but still whatever the system pressure. It's not going to vacuum. In this orientation, I can actually bring that system into vacuum if it's a big enough pump. And any of the commercial pumps we've been talking about, and you guys are going to get involved, they will happen all the time. So we don't want to do that. Potential problems: vacuum, vents drawing air, air release, possible boiling. Like if the water temperature is high enough and all of a sudden you drop that pressure on that water, it can flash. And then if it flashes near the pump, it can cavitate. And all of a sudden you're off to the races on damaging your equipment. So sizing and selection of the expansion tanks. What do you need? What's the fluid? Typically going to be water, might be water and glycol, especially chilled water or whatever the applications might be using, some type of ethylene or propylene, polypropylene, glycol. This is a very important factor. What's the system volume? That's a very important number because that's going to impact what's the expansion of that volume. If it's 10,000 gallons or 5,000, there's a big difference. Fluid temperature at time of fill, fluid temperature at operating. So I fill it when the, with systems cold. That's pretty standard, industry standard. 50 degrees, 40 degrees street water, 50 degrees street water. Fluid temperature at operating. Okay, what's my aquastat? Set for 180, set for 200, set for 160. What is it? All right. Anyways, what do we need to size an expansion tanks? We started talking about it. But water, glycol water, what is the mixture of the fluid? What's the volume, temperatures, fill pressure, and then our relief valve setting. Let's see here. So I thought at the end of the day, we should get into a deep dive of a formula. I'm kidding. But behind the scenes, that really was a lot of the information that went into it. But they considerations for simplification. So isothermal. Remember we talked about that little thermal siphon dip piping arrangement? Some of that's getting into isothermal, constant temperature conditions in the tank, take away heating up the tank and the expansion and all of that, and all those factors that could affect. So the expansion of the tank and the water is ignored. Air cannot escape from the tank. System fills slowly, and ignore the volume of air liberated during heating because we're going to have an air separating device that's going to catch that air and get rid of it. So when you simplify it, really it's that net expansion factor we were talking about earlier times the system volume, and that number is divided by just a couple of pieces of information we need when we design the system and then select it. Meaning, design tank fill pressure in absolute, and then what's the final tank pressure in absolute? 1 minus that. So you kind of plug in a couple of numbers and you get two answers here. One of them is going to be, okay, that 1,000 gallons heated at 200 degrees times it by 0.035. That's the volume of water, 35 gallons of water I got to account for. And then what's my fill pressure and what's my relief valve pressure? So what's my starting point? Because that's a certain amount of pressure sitting on that relief valve. And then what is the relief valve setting? So there's that range I got to play with. So I got to do two things. I got to absorb the volume of water. I got to have a place for it to go. And in doing so, I got to make sure that my pressure increase doesn't blow the relief valve, because then it defeats the purpose of why I specified and put in an expansion tank. So they just got a couple of quick examples here, but a water only fill temperature 40 degrees. Someone's already done the calculation in this example. And they said, look, I got 2,600 gallons of water. The design operating temp is 160. They've designed it on a 30-degree delta T temperature drop. in this case. At the high point, I've got that 4 pounds of positive pressure, and my relief valve down in the mechanical room, in this example, is set for 50 PSI. So you start filling in some of the, conditions, water only 2,600, 160, et cetera, et cetera. Okay, static. What's my height divided by 30, add my positive. Okay, I got a pressure reducing fill valve set for 34 PSI. And again, I had mentioned to you earlier, this and this tank and this relief valve, they're all, generally speaking, pretty close elevation-wise. They're pretty close to each other. They're all sitting right near each other. In this example, they're going to kind of spell out the technical differences between where the relief valve sits, what's the additional pressure sitting on it, where's that feed valve, is the tank connected a couple of feet above or whatever. But generally speaking, as we go through it, we're making the assumption, usually pretty safe, that the relief valve, the fill valve, or pressure reducing valve, the expansion tank connection, they're all right near each other on the same plane. So you start kind of plugging in some of these numbers. Required tank pre-charge, because the tank, technically what they're saying is it's not sitting right down here, but it's actually 9 feet above that. You're going to, instead of 69 feet, it's 60 feet divided by, so I'm going to have a pre-charge of 30. You kind of work your way through these examples. One of the things just to be aware of is relief valves. In this case here, say we got a 50-pound relief valve. It's just known in the industry that the spring tension, the diaphragm spring tension on that relief valve will actually start to weep just a little bit before it gets to the, say, in this case here, that 50. So as a safety factor, they'll say, hey, derate the valve when you're doing your selection to 10% below 50. So in this case here, knock it down 5 pounds, so we say 45, just a safety factor. The relief valve still is 50, but they're just saying, traditionally, they just know that it's sitting there, it's almost ready to go, it might start weeping. So if we take that 10% out of the sizing, it just gives us a little cushion to make sure that that valve doesn't open. And so we start plugging in, what our fill pressure or tank pressure, what our final tank pressure is going to be. And we come up with what I refer to as that 1 minus fill over operating absolute is our acceptance factor. So in this case here, we start plugging in that expansion we said was 160 degrees was the average. It works out to be about 2%, so 0.02. And we're going to multiply that by our system volume. Get this out of the way here. So we can see that it's 2,600 gallons times that 0.02 expansion. So we have an expanded volume of 52 gallons. So then when I take that fill in the maximum operating pressure at the tank, it's a 0.16. So I divide that into the expanded volume of 52 gallons. I have a total tank volume of 325. And that's because when I look at the two numbers that I'm working with, they're saying I got a fill pressure or pre-charge of 30 on the tank, but I only have like about a very tight pressure range before I blow off my relief valve, which causes me to have a pretty large tank. So I have 325 gallons, not to accept 325 gallons of water. I'm only accepting 52, but I got a fill pressure and then I got a relief valve. So the air volume, as it's expanding, as that water's coming into that tank, the 52 gallons, it's squeezing against this air. And as that air is being squeezed and the pressure is rising, I just want to make sure it never rises to that 50 PSI. So this is kind of it's a tight example, meaning fill pressure and relief valve are pretty close. A lot of times what might happen, and it all depends on the boiler that we're using, or boilers or heat exchanger, In that case here, maybe it makes sense to get a higher pressure rated boiler, a 75-pound boiler instead of a 50. And all of a sudden I've got this range, and you do the math, and all of a sudden that number goes down. The expansion doesn't change. If the volume's the volume, that's that. Get 2,600 gallons, I heat it from X to 160, I'm going to have 52 gallons of expansion. But if I have a wider pressure range to play with between fill and relief, then maybe I can reduce that size. Let's see here. So 325 gallons is my total tank. When I start looking at some of them, in this case here, a B series, which I refer to as a full acceptance, my minimum tank volume's got to be greater than 325. In this case here, the B 1400, which is obviously a good sized tank, can handle up to 370 gallons. That would be the model number that would meet that set of conditions that we just went through. 2,600 gallons, 40 degree, up to 160. What's my fill pressure? What's my relief valve? Plug in those numbers. This is what I need. If they went to a D series, which is the diaphragm style as opposed to the bladder, what you'll notice here is they'll say, hey, I can use this D280. And you say, well, wait a minute, the total tank's only 211 and the acceptance is 171. Well, the 171 is fine because I'm only expanding 52 gallons, but I need that total tank. You'll notice on the column here, I actually say, oops, I need two of these. So two of these diaphragm style tanks or one of these larger bladder style tanks to meet the overall, because there's two conditions: volume of water, what am I heating it to? Fill pressure, relief valve. Those two factors I have to meet. If I went to my SystemWise, I went online and used my SystemWise calculator, which we can do in a second. When you get to that SystemWise, you'll have a selection of what am I trying to size? Am I sizing pumps? Am I sizing suction diffusers, et cetera? We go all the way down to expansion tanks. And when I get there, what's my application? Heating, HVAC, heating, cooling. Is it potable water? Is it well water? So in this case here, I'd say, hey, I'm doing a heating application, heating, cooling, HVAC. Tell me the conditions. Fill temperature, 40. What's my max? What's my tank? What's my maximum tank, which is typically my relief? What's the volume of water? So I plug in all of this information. And so we'll do that here. 40 to 160, 30 on the tank, max pressure on the tank, 39, I think it says, 2,600 gallons. So then it spits out real quickly the volume that I need of acceptance and then the total tank volume, which was the numbers we saw earlier when we did the math. And then it'll start, it'll start listing. You say, okay, give me the results. What tanks do I need? So it'll give me all different styles: bladder, diaphragm, in this case, one bladder, two diaphragm, another two bladder, etc. 3. So how do we want to configure it? And Will had mentioned it, earlier, just because that one big tank can do it, maybe we got to consider some other things. How do we get it in? How do we get it out down the road? Maybe it makes sense. 3 smaller tanks versus one big, what have you. Each job, each mechanical room, each application. But it's just to be aware that whether you're going with these 3 smaller or the one big or the 2 different style diaphragm, at the end of the day, what's my expanded volume? And then what's my total tank volume? And how that's determined is what is my fill pressure when I start and what's my relief valve. That's my pressure range I get to play with. And the greater the range, the smaller the tank. The tighter, the bigger the tank to accept that. Maybe Will can speak to that a little better, but the diaphragms are typically in a smaller water volume, smaller expansion, and less expensive, technically, ASME versus going to bladder. But you get to a certain volume size tank, economically, it just makes more sense to go to the bladder at that point. But it's system volume, typically. What's the total expansion? So on the smaller sizes, smaller systems, you'll typically see a D style, a diaphragm ASME. And then when you get into that larger volume, like 2,600 gallons, it might make more sense to to be moving to the bladder. Sometimes to that point, sometimes a conversation comes up, well, the bladder, you can service it. We've had that conversation, sounds good, but maybe that's not a factor in selecting, I don't know if you have any other, that for the most part, right? Right here, where they just give us a quick example to say, well, wait a minute, it's not water anymore. Now we're going to use some type of glycol. So in this case here, the system medium is not water. We just do that drop down arrow and say, hey, instead of water, we want propylene glycol. And as soon as you do that, it'll say, okay, what's your percentage? What's the makeup of water glycol? So in this case here, someone selected 30%. So then again, you hit get results. Now you're dealing with the properties of glycol and the expansion. And look at what happens. That tank went from 325 and 52, 54 to 560, 558 and 93, 94 gallons. So that could be an oops. You definitely want to remember that you're dealing with glycol if you're using glycol. And then if you're not, you're not. But they do have an impact on expansion, which is going to have an impact on what size vessel to support that expansion. So then you go, when you select it, you say, oh, look at that. I'm going to a B2500 if I went with one tank, or a B1200 two tanks, 3 of those 280s. So some of the questions that might come up, we kind of already started talking about, but will a single tank fit through the doorway? How much heavier is it? So you start getting into, shipping weights and what we're wrestling with and all of that. So just things to be aware of. Just because that one big tank can do it, there might be a lot of other physical restrictions or limitations that might make us think, hey, even though it's 3 tanks instead of 1, it's going to be easy to get in, easy to service, easy down the road. So things you want to be aware of. Yeah, that's always another factor. How quick. So where do we locate air separators? Warmest water, lowest pressure. The larger the allowable pressure range, fill valve and release, the smaller the expansion. We always want to make sure that we pre-charge, we adjust the pre-charge before installing it, before we connect it, make sure the mechanical has, pre-charged it appropriately. And the last bullet, best practice, definitely pump away from where that expansion tank is connected out to the building. Let me see if I can do this without reinventing the wheel. Stop sharing, that is correct. Let's see here. Will, can you see that on your screen, that primary, secondary? So just kind of move into a piping strategy that's very popular, has been around a long time. I don't think we have time to really get into the history of it. We just want to talk about what is it, what's going on, and how do we use it, or how is it used? And as you get involved with designing and selecting and what have you, whether it be chillers or boilers or whatever the case may be, this is a popular piping strategy to use to incorporate, brand new, addition, whatever the case may be. It's just more about understanding. And I had mentioned earlier a couple of the design manuals. This next one kind of really covers soup to nuts this conversation about primary, secondary pumping, that TEH 775. Let's see here. And I'm going to move through it. What they're trying to show here is, I don't really like how that sits up there. So when before primary, secondary, or in this case, maybe just instead of primary, secondary, if I have a bunch of zones, and these zones could be buildings. So I have the central plant, I have this distribution pump, and he's responsible for feeding all of these, whatever these are, terminal units, zones, apartment buildings, college dorms, whatever it is. You know, how much pump head does this one distribution pump? Because it's responsible for getting flow everywhere. And so in this case here, as you're looking at the individual zones or loads, you're going to say, hey, this pump's got to be able to support both the pressure drop right here in the mechanical room that's common to everything, everybody. And then in this case, the location, the building, the branch that has the greatest pressure drop. So technically that head, that pump head is really too much for these other branches, but it's needed to support, in this case here, the guy with the greatest, the furthest, perhaps. And so what is it? What is primary, secondary? That's a kind of a loaded question, but we're going to try to jump into it. Convert a large, complex system into smaller, manageable subsystems. So here's my source, chillers, boilers. Here's my distribution feeding all of these various loads. One large pump. And maybe they're zoned with valves of some sort. And maybe I convert it. And what I say is, hey, here's my source, here's my smaller distribution. And then each building, each room, each zone, whatever it is, has its own smaller pump that's, when I say smaller, it's sized just for that one load. So kind of in a way you go back here to these individual, what are the flow and head losses of just these buildings here, instead of having the flow from here for everybody and then overcoming the pressure drop of the largest. I just might have these much smaller. And David, you had mentioned earlier the word decoupling. And sometimes they'll reference that right here, this little common pipe that's common to this loop, and then common to, we'll call it maybe the secondary loop. And they're decoupling them by keeping those T's close together. I don't want to get in, we're just, there's too much, and there's too much to cover and not enough time. Let me see if I can do this. I want to jump ahead just a little bit and get to some of the rules of thumb, if you will. Let's see here. I am share this. Okay. Oops. In that manual, and when we talk about primary, secondary, and we say, hey, we're going to do this decoupling, we're going to use these smaller pumps. One of the, I guess you'd refer to it as a rule or fundamental rule, is when two piping circuits are interconnected, flow in one will cause flow in the other. So two piping circuits interconnected, flow in one will cause flow in the other. To a degree, how much? Depending upon the pressure drop in the piping common to both. So they're trying to show a little piping circuit here that had some really fancy old fittings called monoflow fittings. And the monoflow fittings created pressure drop in the main. And as water was moving along the main, because of these nozzles, these little cones, they would create some pressure drop. And some of the water would say, you know what, I'm going to go through this secondary piece of radiation instead of staying along the main. So flow in one circuit can cause flow in another circuit if you have pressure drop in the pipe that's common to both. If you eliminated that pressure drop, and that's what we're trying to do, is we take those T's, supply and return, and we get them close together, and we eliminate the pressure drop. When two circuits are interconnected, flow in one maybe will not cause flow in the other, because the pressure drop here is now gone. So there's really no motive force to overcome this piping and the frictional resistance at a certain flow rate. I'll just stay along the main. I've isolated, I've decoupled it, I've hydraulically isolated. And now I need a secondary pump or a tertiary, but I need a pump that's sized just for the flow rate and just the pressure drop of this circuit right here. I don't care about the rest of the campus. I don't care about the rest of the buildings. I just need a pump to handle this load right here. So I might have a distribution pump that feeds flow to all the buildings, but then I size the secondary circuit, secondary pumps, just for the flow and the pressure drop of that one, in this case here, this one circuit, this A, B, C, D. And when this pump is off and this pump's running, because I've decoupled it, I've reduced that pressure drop, flow will not take place in this off circuit. So I'll get some control as well. So a couple of rules of thumb or things to be aware of. This decoupler has also been called over the years the common pipe. It's common to both circuits. Call it this distribution circuit and this load or this secondary circuit. So years ago, it's a kind of a rule of thumb. It's pretty safe, but 3 to 4 pipe diameters between the T's is a number to work with. Keep that pressure drop, the head loss, less than 1.5 feet. So as you get into like big chilled water boiler chiller plant, and you've got, I don't know, 16, 20-inch diameter pipe, I mean, massive, and you get tens of thousands of gallons a minute. You're not keeping T's 12 inches. That's way out the window. And that's okay, because it's still the same principle. So all they're saying is on that set of T's, in between that T's for that big piping, big plant, and a certain flow rates, try to keep the pressure drop below about 1.5 feet ahead. And that will achieve that decoupling effect so that I don't get flow where I don't want it unless I bring on a secondary circuit. So they're just showing a real quick example, a 1-pipe primary secondary. That's an option, 1 pipe. And all they're saying is 1 pipe, 1 primary main, and he's feeding a bunch of secondary circuits, closely spaced, closely spaced, closely spaced. Here's my common. Each secondary has its own pump. That's a primary secondary example. Here's another one. Now it's instead of a 1 pipe, it's called a 2 pipe. What's the difference? Well, I still have my primary pump feeding this loop, if you will, this branch, but now I have what they refer to as a crossover bridge. And the real benefit here would be this: whatever temperature, chilled water or hot water that I'm feeding is the same here, is the same here, is the same there. Here, I have some type of load occurring. I'm either cooling, heating up the chilled water, or if it's a boiler plant, I'm taking temperature away. So now I'm dropping my supply temperature to the next, to the next, to the next. I got to account for that. If I use this 2-pipe example, it might look a little more confusing initially on paper or a little more complex. There's a lot of operational benefits to move in that direction. So that anything happening upstream, downstream doesn't affect any of my radiation. It's all seeing the same design water temperature. The only difference between here, 2-pipe direct and 2-pipe reverse, is I've added this extra leg to try to balance one circuit from the other, from the other, from the other. If I stay with this 2-pipe direct, I really got to do a good job with these balance valves to make sure I don't short circuit over pump my closer zones, my closer buildings, and then starve my far remote. One of the ways is if I introduce that reverse return, I provide a little bit of balance. So I'm feeding each building, fairly close to what it needs. When you get into primary, secondary, all it's talking about is, hey, wherever that loop is, wherever your expansion tank is, and that point of no pressure change, when you add your secondary circuits, make sure you're pumping into the secondary circuit so that you'll get the same benefits that your primary pump does by pumping away from the expansion tank. So it's just adding pressure into pressure. You don't want to do this where you put that pump on the return side of that secondary. Now you turn it on, you actually would experience that drop in pressure. You don't want to do that. You always want to have your secondary pumps pumping into your secondary circuit. So this little relationship, they call it the law of the T, but the flow rate, gallons a minute entering a T, must equal the flow rate leaving the T. And that's what you start getting into, different GPMs and how can you have these things, how can they coexist? Well, that's the benefit of that, eliminating that pressure drop, decoupling that common pipe. So I got a quick example here, and they're saying, hey, a direct return primary, secondary, I got 200 gallons a minute on the primary. I got one load here at 70, 55, 30, 45. And then what's taking place at these T's right here at the common pipe? So in this case here, when my primary flow is equal to the secondary, so I have 200 gallons a minute, I've sized this balance valve to provide 70 across the common, across the crossover bridge. When they're equal, 70 into that T, that secondary pump's pumping 70 gallons a minute. He's taking the 70 gallons a minute, returning it. Technically, there is no flow taking place in that common pipe when that secondary pump is on. So this pump's running, say, all the time, providing the flow. When that pump's on and they're equal, there's no flow going here. It's 70 into that T, 70 through the secondary circuit. You shut that pump off, all of a sudden they got 70 across that common. That happens instantly. Another example would be, say, the primary flow is less than the secondary. So in this case here, maybe I'm pumping 55 gallons a minute on this side, and I'm only providing 40. I'm going to get some mixing. So how's the mixing take place? Well, in this case here, if I'm only providing 40 and I'm looking for 55, that 55 that comes back, 15 splits and goes backwards. And it mixes. That's why they call it a mixing T. 15 of a return temp blends with 40 of a supply to get a mixed 55 going out to my secondary. That will take place. That happens all the time. Multiple boilers. So reverse flow in the common pipe. Secondary supply, this 40, whatever that temperature is, can't be this 55 temp because I got some blending. I got some mixing. The return temp, what's coming back from here, has to be the return temp on the primary, because I'm taking that return temp and that flow rate with whatever the temperature is, and I'm intentionally, some of it's going backwards. So whatever doesn't go backwards, that is my return temp coming back. And then the last example would be when the primary flow rate is greater than the secondary. And you say, okay, the forward flow in the common pipe. When it was less, the flow was backwards. When it's more, I'll have 45 entering that T. I only need 30. So that's what that secondary pump is sized for, 30 GPM going through. So the other 15 moves across. Notice how this becomes my mixing T on the return side. So my 30 goes out, goes to the secondary, goes to the terminal units, maybe experiences a temperature drop. It blends with the 15, and now I have a mixed 45 gallons a minute. So I'll have the flow rate will be equal, I'll have the flow rate will be less, and I'll have the flow rate will be more in the primary. Those happen all the time, whether it's pillars, whether it's multiple boilers. There's all different examples where that can occur. And the way it can occur with two different sets of pumps is I've decoupled those pumps so they almost don't even know each other exist, because that pressure drop right here between these T's is basically eliminated. On that example there, 45 gallons a minute, all of a sudden that pump, say whatever, for whatever reason, the load satisfied, that pump shuts off. That 15 gallons a minute immediately jumps to 45 in that circuit, in that one example. So those things are constantly occurring. Just a real quick note, gravity circulation in secondary circuits. If I've got hot water moving across this common pipe here off of this bridge, and the secondary pump, for whatever reason, happens to be off, they can actually experience sometimes on that open T, you might have a little bit of heat migrating. Heat will migrate and an equal amount of cool will come back. And the way they address it is they'll say, hey, we really want to put flow control valves, checks, not only on the supply, which everyone's used to, and they always put them on the supply, put it on the return as well, and it will prevent that. And then the only time these checks will open is now when I turn that secondary pump on. So you can use it for temperature control. And it gets into a little bit of math, but all it's saying is it's like a mixing valve, right? I mean, that's what it is. So I got some hot, I got some mix, some cool, return, whatever. If I was doing a shower head, perhaps, I got some hot coming out of the water heater. I got some cold blending at that mixing, and I got a mixed feed. I'm doing the same thing on these individual circuits. So I got a required, what's the required crossover flow rate? So I got this hot water main, and I got a hot water return main. And I got this crossover, and I'm trying to satisfy a certain load up here. What do I need? What are my flows? What are my temperatures? So you start plugging in conditions. Say, hey, as an example, the secondary load up here is 300,000 BTUs. Whatever it is, snow melt, it's a building, it's heating, or whatever. Requires a supply temp of 150 degrees with a design delta T of 20. The primary supply, what's coming out of the boiler plant that I have available is 160. So what that's asking us is, okay, what's the required crossover bridge flow rate? How many gallons a minute of this 160 do I need to provide 300,000 BTUs at a temperature of 150? That's where the math comes in. That's where that little system sizer from B&G can be a really useful tool, or just use your calculator. But you say, okay, what's the required crossover flow rate? So here's our example. 150 with a 20-degree drop means it's coming back at 130. It told us that we had coming out of the boiler plant 160-degree temperature. So I got 160, I know, coming up. I know the return has to be 130. Why do I know that? Because what am I trying to do with that 160? Am I trying to increase it or decrease its temperature? I want to send out 150. So I want to lower it. I want to do that mixing thing. So I want to take some of my return water and I want to go backwards. I'm going to mix with the 160 to get 150, which means that 130 coming back, whatever doesn't go that way is coming this way. So that tells me across this bridge, what's your delta T? Just on the bridge. Not up here on the secondary circuit, but just on the bridge. 160 on the supply, 130 on the return. Got a 30-degree delta T. Then you say, okay, to figure out GPM, we already talked about this. Started on week 1, focused it on last week. Take my load, divided by what's the 500? Weight of a gallon of water times 60 minutes in an hour, making the assumption we're talking water, specific gravity, specific heat of 1, times my delta T. So in this case here, it's 30. It's just 30 right here, just across the crossover. So I'm taking 300,000 BTUs away through the secondary circuit, whatever it is, big makeup air coil. I don't care what it is. But the flow rate that I need is 20 of 160. And that 20 is going to enter that T. And I got a pump that's pumping how many gallons a minute if it's 300,000 BTUs at a 20-degree delta T? What should the secondary pump be sized for flow? All right? You can either do the math and plug it in again. You can look at your wheel. You can say, I don't know, George, give me the answer. It's getting late. So it's 30 gallons a minute. So I got a pump pumping 30 GPM, and I got a requirement of 20 off of this main, 20 of 160. So I'm going to have 20 of 160 enter that T. I've got 30 GPM going through here. And I'm going to take 10 and I'm going to move backwards. I'm going to blend with the 20 of 160. It's going to give me a mathematical equation. It's going to tell me I'm providing 30 of 150. And then as that 30 comes back, because 10's going backwards, 20 is going back at what temp? Like we already talked about, 130. So there's my math. I got 20 GPM at a 30-degree delta T, represents 300,000 BTUs. I got 20 gallons a minute of, 30 gallons a minute of a 20-degree delta T that represents 300,000 BTUs. So off of my distribution, I've provided it, the system's absorbed it, and the primary has experienced that loss by saying, hey, I come in at a flow rate of 20 at 160, I left 20 at 130. Where'd those 30 degrees go? That load up there. So you can just mathematically say, hey, 30 times 150, right, is what you're chasing after. That's my design. And the way I'm getting there is 20 times 160 plus 10 of 130. I add those two numbers. There's a balance. There's a heat balance equation. So anyways, there's all different formulas. And we're beating ourselves up here, but all of that exists both in this PDF format of this PowerPoint and this manual. And I'm showing these little small numbers. Make them 1,000 gallons a minute. Make them 1,500. Make them whatever you want it to be. It's going to change, but it's the concept of decoupling different flow rates. I can use that. And like if I have a multiple boiler plant and on a really light load, I have 3 boilers off and I have 1 running. And I have a distribution main that's maybe pumping at that design flow. And I'm mixing a little bit of hot water from 1 boiler and the other 3 are off. And then between the return temperature and this hot boiler, I got a mix. And it's October, November, and it's 42 degrees out. I'm in a reset schedule. All I need is 140 degree water. Perfect. And then that will change as that October becomes December, becomes February. And all of a sudden, maybe I need more of my plant. More of that flow is being injected to get that design 160, 180, 190, whatever I need on that really cold day. That's what's happening in all of these connections. So when we say, hey, put in a multiple boiler or put in chillers, 3 or 4 chillers, 2 or 3 chillers, connect them to the system with their own chiller pumps to my distribution, decouple them with my common pipe. I'm getting all of these features, all these capabilities without having pumps fighting each other. Because that's the concern, is you just don't want to put pumps right in series with each other, because typically they're not going to be the same size, and that can wreak havoc. One bigger one will really affect, damage a smaller pump. So here's just, kind of going through the exercise, but instead of, if I had it, what do we got here? Primary flow, 30 gallons a minute, 180 is less than the secondary, 50 gallons a minute. What do I need? I got 30 at 180 and I have 20 at 130. So I have a blended 50 at, you do the math, 160. That 130 coming back. So there's my 30 degree delta T. So I get all kinds of examples, or they have all kinds of examples of how to use that mixing of different flows and different temperatures. Again, primary flow maybe is greater than. So what's going on? That 45 enters, I'm only pumping 30 GPM on a 20 degree delta T, 300,000 BTUs. 15 of that 45 moves across, and it's going to blend with that 30 coming back. So, then I've elevated my return temperature. Instead of 120, it's 127. Why? Because I have a certain amount of that 140 that didn't do any work, because he was pumping more than the actual load needed. So I'm going to elevate that return temperature coming from the secondary. That 120 becomes 127. So common pipe. So this common pipe, size it for high delta T design and primary piping, perhaps. If you have a scenario where these flow rates on the secondary are much higher than your your crossover, then these are just little piping techniques to prevent any kind of induced flow. Upstream of the T, downstream of the T, there's these little rules that come about slowing down the velocity. So I have some proper mixing and not increasing the velocity. And again, you start getting into some of these applications. This is very common. We get involved with this a lot, injection pumping, where I have a heat source and I have a load over here. And instead of maybe using a valve, I might use an injection pump. And that pump is going to take some of this hot water and inject it in an equal amount of return water back. Whatever doesn't get injected back moves across that common. I've got some blending, some mixing right there. So I can do all kinds of things. We do it all the time. There's little details on this piping arrangement, on how to handle it, how to do it properly. Some pressure drop. It's typically some very short pieces of pipe. We want some pressure drop typically to have some type of circuit set of balance valve to create some head, some restrictive head, because really I want this pump to be working against something. If it doesn't have that resistance, it'll move out on a curve. I want to back it in. Instead of using pumps, they'll use valves. This is very common. There's different ways. Here I've got, what I call this a one pipe or a two pipe primary secondary. This arrangement here. This would be referred to as a two pipe because I have this crossover. So I have the main running along. I cross over to feed building 1, continue along, same temperature, feeding building 2, and then so that's a two pipe system. And what they're trying to show here is there's different ways of using a modulating valve instead of an injection pump to provide different water temperatures. And those could be based on reset schedules or, whatever the application is, make up air coils, maintaining a certain discharge air temperature. When you get into three-way valves, which is an option, it's a design option, what they're going to talk about is there's 3 different ways to do it. The original, kind of old school, the preferred, and even the better method. And just real quickly, kind of looking at it intuitively, what changes if I start here and say, hey, I got this mixing valve that's up on the secondary circuit, the load circuit. Why do they maybe say, hey, this is a better way than putting the valve? Because the mixing still takes place at that T. This becomes more of a diverting valve, but it mixes right there to get that desired water temperature. One of the concerns is when that valve goes to close and says, hey, I don't need more heat. I'm okay right now. And I close off that port. As the temperature drop takes place, I'm missing my pressurization. I'm missing my expansion tank. And I can have some rapid drop in pressure in that closed loop. So they said, hey, move it over here. So now I'm always seeing, even through that check valve, but I'm moving in the right direction. So that check's open to the system. I'm seeing pressurization. So that's an improvement. But both of these valves are in the load circuit. This third and final one, they're saying, hey, let's take it out of the load. Let's put it back here on the crossover. Now the valve is actually controlling the flow that I need into that system. Up here, I'm sizing this valve based on that size of that pump. What's his flow rate? But the actual amount of flow that I need might be pretty low that I'm sending across this crossover or across this one. So instead of putting the valve up here or up here, let's put it over here on the crossover. Now it's much smaller because now it's truly, hey, over here I'm pumping 20, I'm just throwing numbers at you, 200 gallons a minute, I'm going to inject 10 or 20 or whatever. Well, if I'm pumping 200 GPM and I have the valve over here, that valve's got to contend with 200 GPM. Regardless of the port's moving, it's 200 gallons a minute. If I move it down to this crossover, the maximum he's seeing is that injection flow rate of 10 gallons a minute or 20. I could be a much smaller, more accurate control valve. And this will do his thing at that 200 gallons a minute. And he's just seeing, because what's happening is that hot water moves across, that port starts to close. What's its only option then? It has to go this way into that circuit. And as it does that, an equal amount of return water goes this way through the return port and back across the crossover. So it's a nice clean way of providing control. So again, there's all kinds of applications, if you will. And again, these might be little zones. These could be buildings. Here's my distribution, crossover. I could have control valves. I could have variable speed on this distribution if I wanted. There's, again, all kinds of examples. I could have on-off pump. What that means, I'm cycling the pump on and off based on a requirement. Maybe I have this pump running continuous. You say, well, if I'm running continuous, aren't I going to potentially overheat? So the way they address it is they have these three-way valves. And the three-way valves are kind of like a two-position three-way valve. I'm flowing through the terminal unit. This port's closed. Base temperature says, hey, I'm satisfied. I close that port. I open this. Now I go this way and I bypass the terminal unit. It's another way. Kind of consuming a lot of energy. Maybe I want to do variable speed. And I sense as these control valves close, I speed up or slow down my variable speed pump. That's probably more common today. But there's all these different options. And I've got this primary main, this primary return, and I'm connected through this common pipe. This green pipe is my low pressure drop, my common. And you notice it's not showing these little closely spaced T's because when you get into the real world, there's going to be some separation. Just remember that 1.5 feet of head loss, whether you're dealing with 3/4 inch pipe or 16-inch pipe. If I can keep that pressure drop very low, I've achieved my decoupling. And again, they're just showing some examples. You'll hear the expression primary, secondary, tertiary. And what that's leading to is, again, don't get into the argument of is that primary, is that secondary. This is my production, chilled water or hot water, primary, they're calling it. I have my secondary, which is my distribution out to the campus. And then I have my tertiary or my load pumps that are in the individual apartment buildings or dorms or classrooms or whatever it is, wings of a hospital. So I have primary, secondary, tertiary. So I have a common pipe to isolate, hydraulically decouple this pump from this pump. And then I have these common pipes to decouple this pump from these tertiary pumps. Yes, sir. Yeah, exactly. That would be a distribution hot water pumps, and then that might be your individual radiation pumps going to make up air coils, going to apartment building with 48 apartments with thermostats and a zone valve all the way up here, and you've got a variable speed, ECM pump. You could do that. So they simplify the drawings. It's your imagination and application. It's really getting the concept of decoupling and all the benefits versus trying to do all of this with this one big pump with this really high head. And then I got all of these control valves that are trying to open and close against a really high differential in a maybe a excessive horsepower requirement. So maybe I can start using these smaller pumps, and then when I add up all the horsepower, it's not excessive, it's actually less, and it's smoother control because I'm using smaller headed pressure differential pumps that are size specific to their necessary loads or needs. Here they're just showing an example where maybe I can incorporate primary, secondary to do an expansion. So I have this existing source, distribution, heating or chilled water going to some loads, and all of a sudden there's a renovation, I got an addition. I can tap in, obviously I got to make sure I have the capacity to support, and this piping here, or this flow rate, if this piping is size, sometimes what they'll sit back and they'll say, hey, if I increase the temperature here, I can take a bigger delta T. I can now support these additional two buildings or crossovers to support the new load. It's a clean way of adding capacity. This might get a little more light commercial in an apartment building, a church, a school, even sometimes residential homes. But they're saying, hey, just by using this technique, this primary, secondary, I can provide some priority to the indirect off of my boiler that's also feeding my heating system upstairs. So you say, well, how do I get priority here? Well, if I pipe the hot water supply to the indirect, and that indirect is very similar to that tank that's sitting right over there next to you guys on your left. It's a cutaway showing the coil inside, but the vessel has your potable water that's going out to your tub, shower, sinks, and then the boiler water goes through the coil to heat the water. So that's why they call it indirect. There's not a flame underneath it. The flame is sitting over here. So I'm kind of indirectly heating with boiler water. But the priority part comes with this piping. If I pipe it this way and this pump is off, what's the flow through this if this pump is off? It should be zero with closely spaced teeth. So I'm just going to flow through. Here's my boiler pump here, doing this. And then all of a sudden, the domestic call comes in and turns that pump on. Now, all of a sudden, I'm taking hot boiler water through the coil, heating up the water, taking a delta T, a temperature drop, putting it back on that loop. So there's my priority. I'm grabbing all the energy that the boiler has right off the bat. Whatever temperature drop I have left, that's when I'm feeding my zones, perhaps. But I prioritize it just by the location and using closely spaced teeth. So this boiler pump here isn't fighting. It doesn't even know this pump exists. Neither one knows the other exists because they're decoupled right there. It's just an application. It's a way of plugging in using primary, secondary. It could be multiple boilers. You can use it for temperature control. You can use that. Here's an example of that low loss header. This guy here that we were talking about earlier. Primary, secondary connections. Here's the example that, yeah, I can use it as an air separator, but I'm also using it as my primary, secondary teeth. So I've decoupled the boiler plant from my system. And then from there, I've got, you know, a domestic hot water. So maybe I want straight boiler water to heat the domestic whenever there's a call. Maybe I have this piping arrangement with that injection pump because I've got some snow melt or radiant heat. So I didn't need a different water temperature going through the tube. And you can just isolate, decouple right here. And then I have these zone pumps, domestic, injection going to radiant. And then whatever the case is going on over here, I decouple it with this crossover right here, or this common pipe, I should say. So there's just, you know, there's all different applications you can come up against. Say that one more time. So this is your indirect pump, Dave. Yeah, he's not calling because the tank's satisfied. Yep. Meaning this, the boiler pump? Yep, okay. No, because that is just like a closely spaced set of T's. So the flow that will be occurring will be a function of if these guys happen to be still calling. But if he's off, the only flow is going to, you know, whatever the GPM is. So this pump's doing his thing, then all of a sudden this pump is running and he's taking X number of gallons a minute. So he injects whatever X, an equal amount of hot water is now moving in this direction, but it can't go here because it's trying to get to the suction of that pump. So I'm going to have this water moving across this T. I'm checked, the pump is off. I'm moving along just like a zone pump. I've got 3 or 4 zone pumps. One's running, the other 2 are off. I could have heat going across here, but that heat is not migrating down, and it's not going to be induced by the flow of this pump. So unless that pump turned on and created its own set of pressure differential, and now he's saying, hey, I want some flow through here. I'm coming back to this T, plus I add up this. So now I'm injecting more GPM, perhaps more hot water, cool water is moving back here, which means more hot boiler water is moving out here. Oh, if this was just, if you took that red pipe and connected to that and that to that, it's exactly what would happen, just what you described. That is now in series, and it's going to go through here, it's going to go through here, and it's going to go through here, always. That's what we're trying to avoid. And sometimes when they don't understand that, they'll set up a scenario where whenever that, I got heat everywhere. You know, I got heat in my zones, or I got my domestic hot water is 180 degrees. The aquaset's not even calling. I pulled the aquaset out because they piped it just like you described. And then all of a sudden, that pump is in series. So it has to go. Now, how much is a function of the capacity of this pump, what's the pressure drop through the coil. Each one's going to dictate the flow, but it's out of control at that point. Correct. That's exactly right. Does that make sense? Is that it's pumps in series, and that whole, whether it's this guy or it's a set of T's, that's not necessarily the greatest picture. These T's here, these closely spaced T's, because if that T wasn't there and this pump just went up into that, if that pump was off and this guy's running, he's going through there. We don't want that, but he's absolutely, because he's in series. So what do you get? What are some of the applications? Large, diverse systems with high cumulative pressure drops. We want to eliminate that by having smaller pump size appropriately. Different supply temperatures in the different zones. I need specific flow rates through my boiler plant or my chiller plant, and I want to decouple it from what the variable speed pumps are doing, because the zone valves out on all the fan coils are opening and closing based on. So let me support my production, my chillers, with the appropriate flow through the chiller barrel, and decouple that to what my distribution pumps may be. So that's what they're kind of talking about here. And then just a quick example where you might have some freeze protection. You've got some constant circulation going through some makeup air coils that are not overheating. If there's no need for heat, you might close off a control valve or such that's bringing heat, but I got flow going through the coil. So as the cold air is coming in, I'm not freezing those makeup air coils. So some of the benefits, perhaps smaller pumps, a little bit of piping, can offer some flexibility, whether it's constant or variable speed. And the goal, which they set years ago when they were first kind of introducing this pumping concept, is they could improve the actual overall energy consumed in the pumping system. So just real quick, anyone get system sizes with them? Everyone's got to sit on the hands. No, I don't got anything. Not me. Just real quick, it's just going through how it works, how it makes sense. So determine the crossover bridge flow rate for this load. 200,000 BTUs at a mean water temperature of 140 with a 20-degree delta T. So mean water temp. So what's the supply temp supposed to be? If I'm taking a 20-degree drop and my mean water is 140, 150 on the supply, and then 130 on the return. There's my 20-degree delta T. The average temp in that radiation is going to be 140. The load is 200,000 BTUs. What's the flow rate of 200,000 BTUs at a 20-degree delta T? What should it be? 20, right? 200 MBH opposite a 20-degree delta T will tell me I need flow rate at 20 GPM. So that secondary pump is pumping 20 whenever it's running, whenever it's being called to do some heating, 200,000 BTUs worth of heating with an average or mean water temperature of 140. So this is pumping 20. So then the only other factor that they told us when we're playing this little game is the temperature available coming from the boiler plant, which in today's world is quite excessive, but years back maybe not as much, is 210 degrees. So I have 210 available, but this is what I want. 150 on the supply at a flow rate of 20, take a 20-degree drop, so I'm going to come back at 130. So then the question becomes, what do I need? What's the crossover bridge flow? What's the crossover bridge return temperature? Now, as I've used these terminologies, we'll look at different pictures. If I'm coming in here at 150 and I'm coming back at 130, and I have over here 210, right? That's what's available. How am I going to, God's name, make 210 150? You got to mix, right? What am I mixing it with? The return temp, 130. So if it doesn't go backwards to mix, that's the remaining flow rate that has to go across. So there's my return temp. So now I know my supply is 210 and my return is going to be 130. What's the delta T across that bridge? 80. Now, when we were talking about designing systems and figuring out GPM and picking pumps and all that, we said, typically 20 degrees, 10 degrees in chilled water. Well, here's an example, and again, using math, using that wheel, where just to move 200,000 BTUs, I'm going to take an 80-degree delta T just across this bridge. So then the question becomes, okay, well, how many GPM do I need? Well, if I know it's coming back at 130, I have a supply. There's my delta T, 80. So let's take the load. Take the wheel, scale 1, 200 MBH, opposite, 80-degree delta T, small white window, GPM. Or take my calculator, 200,000 divided by 80 times 5 GPM. So I need 5 gallons a minute of 210, even though I'm pumping 20. Remember that law of the T? The primary and secondary can be equal. The primary can be greater. The primary can be less. This is an example where that is less. So now that 20 GPM of 130 comes back. What's going to go backwards? 15 has to. And then the 5 of the 130 goes back. So there's my 80. I've moved my 200,000 BTUs across that crossover. Now here's where the magic takes place at that mixing point is 15 of 130 blending with 5 at 210 becomes 20 at 150. Ta-da! Pretty simple stuff, but that's the beauty of being able to mix and match, and taking some really high temperatures available. I mean, it could be anything. That could be a building. That could be whatever you want it to be. It's just the concept. And this whole thing of the primary and the secondary equal, the primary is greater than the secondary is greater than the primary. And that whatever enters a T has to leave a T. It sounds so silly, but it kind of makes it easy to understand. Well, in this case here, they're actually, it's more theory than practicality. But you wouldn't even have a valve. If you had this set up properly, that I had 5 of 210 coming across here, and the thing is I had a load of 200,000 BTUs, and I'm pumping 20 gallons a minute, that's taking place. That's occurring. Now, as that 200 becomes less and I'm still pumping that same flow, I'm going to overheat, right? So I'm either cycling the pump on and off, very discomfortable. So then I'm probably going to introduce almost like this crossover. I'm going to probably put that 3-way valve. Yeah, exactly. Right. And then I'm going to look at the supply temp, and then I might even have an outdoor air sensor that says, hey, is it 40 degrees, 25 degrees out, 5 degrees? What is it? And I'll constantly be repositioning to change that supply temp to do an outdoor reset. But yeah, I could use like a 3-way valve and adjust accordingly. So if it starts to overheat, some of that water might go through the bypass, it doesn't get directed up here. How you guys doing? No, seriously. Let me just go through one quick example. We'll bypass this real quick. Yeah, heat balanced. Okay. Just these are what you're going to see. Multiple chillers. This is a primary, secondary, all day, every day. You guys, your firms are doing this, seeing this, where they might have chiller pumps dedicated to each chiller barrel. The decoupling with that common pipe doesn't look quite like those closely spaced T's, but it actually is perfectly located. Maybe I have a group of 2 or 3 primary pumps that are doing some type of variable frequency drive based on control valves. So 3 little circuits, it could be 300 of them, whatever the case may be. That's a very common application. And I'll be staging these chillers with some type of chiller plant control to say, hey, what's my chilled water temperature going out? What's the load on the building, et cetera. I don't need to get into that right now. Anyways, here's an example. You get into multiple boilers real quickly. You get into multiple boilers. is another example. We do it all the time using primary, secondary. But this is just a quick comment. It's out of one of the authors in the industry, a guy named John Zigenthaler, and he's talking about, hey, when you introduce to your client, your customer, a multiple boiler plant and all the benefits that come with it, well, one of the ways to make sure you achieve or they achieve that efficiency you talked about is when a boiler isn't firing, we don't want any flow through that off boiler because it becomes a radiator. So you start to lose some of the efficiency. So you want to isolate the boilers from each other. So then he'll show this quick example. And again, old technology, it's all over downtown Boston. It's slowly being replaced as we get opportunities, funding, new owners, whatever the case may be. But this is a quick example of a 3-boiler modular system where maybe only one boiler fires to satisfy the load, but I've got flow going through all 3 boilers. So these 2 off boilers become radiators. Very inefficient. You know, and they might be using a stager control. They might be doing aquastat settings that dictate when I come on, when I come off. So it's 40 years ago, 30 years ago, pretty popular. 50 years ago, popular. Because going from this one big boiler to these 3 smaller, I look at the fuel savings, and there was some, but they were missing some. So then they go to these multiple boilers, and they decouple them, and they have the closely spaced T's, and they have the boiler pumps on each boiler. And in this case here, maybe they're non-condensing. So you got to protect the heat exchanger and the breaching, the flue vent piping. So then they introduce some type of mixing valve to take it even a step further. So I get 2 or 3 boilers, then a mixing valve going out to the building. One of the downsides to this is called one pipe primary, secondary. So if you remember, sometimes the temperature can degrade, from one to the next to the next. If I'm heating zones, I'm taking the heat away, I'm lowering my supply temp. If I'm in the boiler room, I'm adding heat. So I'm actually taking one temp and increasing it. That's going to the next boiler. That's going to the next boiler. So here's a really quick example. And when I say quick, I mean quick. Here's 300,000 BTU boilers that replaced one big 300,000 BTU boiler in an apartment building. And the guy pipes like this. He goes, I've heard about this. Isolate the boilers, do primary, secondary. I'm going to do it. I'm going to get 3 smaller 100,000 BTU boilers, each with its own pump. I'm going to do primary, secondary, and I'm going to keep my big distribution pump that handles the whole load out to the apartment. And this is the one downside. And some boiler manufacturers still promote this. They show this in their installation manual, the design manuals. Under design day, when I need all my horsepower, all my boiler plant, 300,000 BTUs at a 20-degree delta T, 190 to 170 is 30 GPM. I got 3 100,000 BTU boilers, each one designed at a 20-degree temperature change. What would the flow rate be for each one of these pumps if each boiler is 100,000 BTUs at a 20-degree delta T? What would the flow be for each one? What should it be? Yeah, it should be 10 gallons a minute, right? 100,000 divided by 20 times 500, 10 GPM. So if I'm in design conditions, I've got some kind of supply sensor sitting out here saying, hey, I want 190. I'm not there. Hey, boiler 1, come on, help me. So then what's going to happen is, think about this. The law of the T, closely spaced T's. I got pumping 30 GPM throughout the building. Now all of a sudden, boiler 1 comes on and his pump comes on. He's designed and sized for 10 gallons a minute. He's going to take 10 off of that loop, and he's going to put it through the heat exchanger, and he's going to pick up energy. And in theory, if he's doing that 20-degree, 100,000 BTUs, what's the temperature of the water coming out of that heat exchanger? What should it be? 190, right? Which is what we're chasing, right? You're like, oh, great, we're there, 190. What's the flow rate though? 10, right? Of 190. What happens when it enters into that T? Mixing in lowers, exactly, because I'm not pumping 10 up here, I'm pumping 30, because the total load is the 300,000, 30. So all of a sudden, when I do my blending and I say, hey, I got 30 of 170, 10 goes this way, gets heated up to the 190, which is what I'm chasing after, but oops, I got 20 at what temp here? 170. So the 10 of 190, the 20 of 170, I got 30 at 177. Stager control says, hey, I told you I need 190. It's cold out. Boiler 2, come on. What goes into boiler 2? 10 at 177, does his job, transfers his 100,000 BTUs, supply temp coming up. Wow, he's actually more than I need. But what happens here? 20 at 177 blends with a 10 at 197 to a blended 184. So I'm still not at my desired temperature. So then I finally kick on the last boiler, and now my inlet temperature is 184. What's my outlet temperature? What should it be? If I'm adding that 100,000 at 10 GPM, 20-degree temperature rise, it's coming out 204. Now what I've done is I've taken each boiler, changed its efficiencies, and I'm elevating the inlet temperature to the next one, to the next one. So it's one pipe, primary, secondary, just like this drawing showed, right here. But there's some downside to that design. And that's that one pipe versus a two pipe. If you look in some of the other boiler manufacturers, this would be like out of, say, Lochinvar's manual. What's the difference here? If I have my return and here's my supply, say that was my 30 gallons a minute, I'm connected with closely spaced T's, but it's almost like a two pipe because I've created this manifold in each boiler. What has its own pump, right? And so whenever the inlet temperature is to the same, if it's coming back at 170 and only one boiler is running, 170 is going, these three are off. If I get to that design condition where I need everything, it's the same temperature all the way across all of these boilers. So I'm not doing that. So I'm 170 to 190 all the way across the plant. Just for argument's sake, if this was my 30 and I was taking 3 instead of the picture of 4, but if I had 3 10-gallon-minute pumps, what would be the flow rate right across that common pipe when everybody's running? What should it be? 0. Exactly right. So in that case, primary and secondary match, they equal, there's no flow through the common. So all of that 170 gets heated, 20-degree rise, comes out at 190, matches the desired flow rate. Stage of control says, hey, you met, wait, perfect. That's primary, secondary. That's with multiple boilers. It could be with multiple chillers. Yes. You just have these two pipes, a supply manifold and a return manifold, each with its own pump and check valve, instead of doing this whole, because what you've done is you've added this extra kind of loop pump that in this case here happens to be feeding a four-way valve. But yeah, there'd be an easy way to fix that. Yeah. Boop. And then you have to have the return come back over here. That moves over. That moves over. Now you've got your two pipe manifolds, supply and return. They're not seeing each other. That goes away. Yes, that would be a real quick fix. Yeah. We're oh, you guys, you should see what you look like right now. You want to kill us. Well, listen, thank you all very much. Everyone that's been on remote, we appreciate the time. Everyone here physically, we thank you for coming. We got one more week. We got Mr. Will Fisher is going to give us some pretty good presentations on heat transfer and heat exchangers, and talk a little about new technology with heat pumps and air source. Should be a good week. So thank you all very much. We'll see you next Thursday. Have a great week. Oh, you're going to Connecticut? Back to Putnam? Oh, Danbury. Okay. Oh, man. All right. Take care. Have a great week. Thank you very much.